Okay, this is better. Zoom always stumps me sometimes. Here and there. One thing would work, the other thing would go.
Yeah. And just when you think you have figured out Zoom, somebody will have a meeting or in some other, I don't know, Teams,
Oh yeah, I
Meet. I mean, there's like a zoo of things.
have quite a few that I've learned lately, and
yeah.
Zoom also sometimes would change its settings, and then they wouldn't necessarily notify us. So it's
Yeah, for me, the problem is because it keeps putting me back to my official, whatever, the academic Zoom account of the institute, which,
I see.
there's some issues. Yeah, so
I only have one, but yeah, that can happen.
Yeah.
Okay, should we get rolling? I should introduce Sudeshna. Thank you, everyone. This is fantastic that we have, one sec. Okay, admit. Oh, who's there? Sorry, I just want to make sure that I can minimize the music as we start. Okay. So yeah, thank you for your patience and for not disappearing completely from this group and joining. Hope you're having a good summer. Now, our speaker today is Professor Sudeshna Sinha. And today she'll talk about harnessing chaos. And Sudeshna is from Department of Physical Sciences at the Indian Institute of Science, Education and Research, IISER, Mohali. Sudeshna has a very distinguished background. She obtained her 5-year integrated master's degree in chemistry from IIT Kanpur and went on to do her PhD at the Tata Institute of Fundamental Research, followed by postdoctoral work at Trieste. On her return to India, she was a faculty member at the Indian Institute of Astrophysics, Bangalore, and then at the Institute of Mathematical Sciences, Chennai, and is currently a professor in the Department of Physical Sciences and the deputy director of IISER Mohali. She works in the field of nonlinear science, chaos, complex systems, and her large body of work has been highlighted in news features, ranging from Nature News and Views in Scientific American to The Economist. I didn't know that. And MIT's Technology Review. She is a recipient of the Birla Award for Physics and was conferred the J.C. Bose National Fellowship. She has been elected a fellow of the Indian Academy of Sciences, Bangalore, the Indian National Science Academy, New Delhi, and the World Academy of Sciences, 3S, not the third word anymore. So please, Sudeshna, thank you so much for being with us, and let's get rolling.
Right. Thank you so much for the very generous introduction. You can see my slides, I suppose, right? And kind of, can you see my slides?
Yeah, slides are right, fine.
Huh? And you sort of can probably see my video also a little bit. Yeah. Okay.
Yes.
Okay. Right. So, yeah. So I was just telling somebody the other day that, there's just one weird positive offshoot of this terrible time is the fact that we have normalized online seminars. So one has managed to cut across geography and time zones. It's kind of after dinner for the bunch of us from India right now, and still manage to meet on this platform. So at least there is one thing I can say which is nice and positive among all the gloom and doom. Okay, so what I thought I'd share with you today was one particular research thread, and this actually involves the use of our understanding of chaos. So not just the phenomena or trying to understand it, but sort of exploit what we have understood already to do something specific, hopefully useful. Okay, and I thought I'd choose this particular research thread over my more purely theoretical musings, just maybe to show that sometimes very abstract ideas and constructs which you just do because you think it's neat, no good reason other than that, but somehow it finds a way into applications, and of course it's fun when it does, because for theoreticians it's not something you aim for, it's something either, if it comes by, you take it and it's fun. Okay, so that's probably why I thought I would share this particular thread. So I absolutely, so I see so many experts in this audience that I'm sort of embarrassed for the next 10 minutes of this talk, but I'll still go through it because I thought perhaps, some of you are not quite in the field. So, I should devote maybe 10 minutes to a very shallow crash introduction to the concept of chaos. Okay, and so my profound apologies to all the experts in this virtual audience. I mean, the host included, Shurajit, I saw Ambika, I saw all kinds, Prashant, everybody out there. But please do just ride along for the next 10 minutes. Hopefully the meat will come later. Okay,
No
since
problem.
it
There are
was one.
students also. I just wanted to
Oh,
mention that.
wonderful. Okay,
Yeah,
so
yeah.
okay, so 10 minutes of apology for the experts, and
This
maybe
is
it's,
good.
and apologies to the students for being only 10 minutes. So both ways, it's probably an apology. Okay, so the basic thing I always like to start with is the following. So we are dealing with classical mechanics. So classical phenomena, I think, is a very polite word for really old. That's what young people say. Classical is, seriously old. Okay, but the point is, to put a spin on Wigner's famous quote, the unreasonable effectiveness of classical mechanics still makes it an extremely relevant, extremely useful tool. I mean, there's absolutely no way to do certain things other than using its framework. And in fact, sometimes I tell my students, it's actually as if it has no business being this good. It is mathematically rigorous, it is clean, and it applies to things over such a large range of length scales and time scales, from nanomechanical oscillators. So I have people in ISA Mohali who have these labs, and they're forever coming to me with their Duffing oscillators and their Van der Pol oscillators, straight nonlinear dynamics 101, classical oscillators, because it's completely relevant to them. And of course, my astro friends are on other side of the scale, extremely large, extremely long time scales, and they too deal with this all the time. So in some sense, you can think of the concept of chaos as a new kid in a very old block. Okay, classical mechanics seriously old, and this is a new kid in the block. But it is a, a concept which has caused actually some kind of paradigm shift, because it has made us fundamentally reassess the way in which we view the classical physical world. You may have thought that was done and dusted, but it isn't. That's the whole point. And the surprise really is that a very large range of seemingly simple natural processes, the word simple is in red for a reason, because if I gave you something very complicated, very complex, like tons of things interacting, and something complicated comes out of it, you might say, oh, well, I mean, okay, you're impressed, but not so impressed. But the whole point is that extremely simple processes can exhibit enormously complex behavior. Okay, that is the surprise. And when I say complex behavior, it is so complex that it seemingly random looking. So if you didn't know better, you might have tried to model it as if it was evolving under random forces rather than perfectly neat, easy looking deterministic laws, okay, which is ticking in the background like clockwork. Okay, so completely deterministic systems, the thing which was caused a lot of unease, was found to display exponential sensitivity to initial conditions. So, what does this mean in real terms? It means that it renders a deterministic system essentially unpredictable. You never thought you would use these two words, deterministic and unpredictable, in the same sentence sensibly. But these two concepts actually though seem to be totally counterintuitive to go together, are, are perfectly well defined in the case of a chaotic system. So this is what made people sit up and say, okay, we have to take a look again at classical mechanics and see what it entails in its full glory. And this is the new science, quote unquote, of chaos theory. So what I find a little fun is the sociology of science. So I thought I'll just say a few words on it. So the word chaos, of course, is has commonplace meaning, right? I mean, in India we use it all the time. I mean, it's there to describe traffic, which is a very good word to describe it. Politics, again, unfortunately, a very good word to describe it. So it's commonplace and it's absolutely used in everyday language, but apparently it's seriously old as well. So when I meet people from other countries, they tell me that they had a word for it, some of it from ancient times. I didn't figure out if Sanskrit had a word for it. Some of you might tell me later. But the Greek cosmology definitely had this word spelled as so. And essentially, it had the meaning of being pre order. So it was the primeval emptiness of the universe before it came into being, before order in some sense. So, not order at any rate. The Chinese also have this symbol. I got this from the internet. I hope it's correct. But I think it is because I'd given some of these talks there. Nobody, maybe they were too polite, but they went along with this. But what I do know is from Hao Bailin's famous edited book of, which we learned from when we were young, that it was a word which was there in ancient Chinese. Of course, if you look up Webster Dictionary, it means confused, unorganized, disorderly. All of these are sort of synonyms of the word, which is why in India describes traffic and politics. But the thing is that this commonplace word appeared as a technical term in scientific literature, I believe, for the first time. The word first is always, maybe quote unquote. But as far as I know, in this 1975 paper by Lee and York, an American mathematical monthly, period 3 implies chaos. So, suddenly a word which you think has no, technical meaning acquires one. And so the header of this is taken from this wonderful book by Ian Stewart on the new mathematics of chaos. Does God play dice? And so the key idea is that the present determines the future. Thank God for that, at least. But the approximate present does not approximately determine the future. This is, of course, terrible news for astrologers, but that is what is at the heart of chaos. So the irregular motion of a deterministic dynamical system that could be, so sensitive to initial conditions that they are impossible to predict in the long term, with anything less than infinite and perfect representation of analog values. So I've written it in this fashion: infinite and perfect representation of analog values to make contact with people who do computations and do numerical simulations. Because, we are in the era of experimental math. So we take, say, a differential equation and we simulate it on our digital computer. So it absolutely depends on how we represent analog values, this real number, say X, in the computer. And what it tells you is that unless you have infinite and perfect representation of analog values, you are in trouble, which is what Lorentz realized more or less, serendipitously at some point. Even old luminaries, who had not really pushed the concept through, had felt unease and had flagged the issue. Even Maxwell, Hadamard, Poincaré, of course, famously trying to nail the three-body problem, did that. Okay, so it has been building up. And now, of course, after decades of people understanding it in many different ways, from applied math to mathematics, of course, as a dynamical systems is a branch of mathematics, to applied mathematicians, to physicists, to chemists, to biologists like Winfrey. It's like gone across disciplines. But it's somehow, I find it interesting that it has come back a full circle, back to popular imagination, back to common folklore, and back to common usage, now with a little touch of the science in it. So, there are bestsellers, which people have written, these are bestsellers which I can't get myself to read because I probably, when you know the subject, it seems a little trite. But, just like my introduction being a bit shallow and a bit of a crash thing, it's okay, I suppose. On to Hollywood movies where, the word butterfly effect again used, like a Hollywood style thing, but it's there in the public imagination. So in some sense, it's gone back to popular usage, enhanced by the science. So I thought I'll just throw a bit of sociology in there. Okay. I'll just have a few more slides for the young people. And that is, I thought I should put at least a couple of equations and one or two examples, which would be probably visual. So a simple, maybe slightly imprecise characterization of chaos then is sustained, disorderly looking, aperiodic, long-term evolution. Okay, I've put in everything that we had before in one sentence. And to get a precise signature of chaos, I would have to estimate this exponent, which goes by the name of the great Lyapunov, the Lyapunov exponent, which essentially gives you the rate of exponential divergence of small deviations around a trajectory. So how much do two neighboring trajectories fly apart from each other is captured by this. And anyone who has tried to estimate this knows it is actually pretty hard to do numerically, because you see there are two limits sitting in here. T tends to infinity, this delta x tending to 0, not easy, not so need to put into a algorithm. So it's not an easy quantity to estimate, but it is the most rigorous signature. So instead of going to that, because it's there, but it may not be so evocative of what actually happens, I thought I'll show you just two examples before I get to the meat of my thing. So as I've been saying, the whole thing which makes it so wonderful is that these chaotic systems can be seriously simple. So nothing gets more simple than a one-dimensional system. Okay, so here is an example of a discrete time system. So it's a map. So n's are integer, so it's an integer time thing, and it just is a function which iterates itself and gives you the value at the next iterate through a nonlinear function. That's it. You can sit with your pocket calculator and generate it. And so here are three examples. The first one just has a quadratic nonlinearity, an x square. So it's a parabola. The second one actually is just piecewise. These two are just piecewise linear. One of them is the binary shift map. It's a very, very nice map because it maps into a shift register. So this is just, you think of it in the unit box 0 to 1 as just two straight lines. Okay, mod 1 means it wraps around. So you can also think of it as being on a circle. And the tent map is like two straight lines like that, like a tent. And this is its time series. Such a simple object out here. This was actually the tent map, I think I drew out here. Yeah, it's the tent map. And this huge mess that you see here comes from 1 minus 2, x minus half absolute value. So it seems as if something seriously simple has given rise to something very, very complicated looking. Something you wouldn't have guessed was generated by just this deterministic map ticking in the background. But it has two actions. And this is the basis of all chaos. One is stretch, that is neighboring things fly apart, which is your positive Lyapunov exponent, a certain way of thinking. The other thing is the fold operation. So the fold operation is a way of putting your trajectories back into a bounded region of phase space. And why is that important? So just suppose you had a linear map, x going to 2x. Then the two things also fly apart. But that's not interesting. There are two trajectories flying apart. Obviously, the distance between them is getting larger and larger. But, where's the fun in that? But somehow, if they were forced to fold back and go back to the same neighborhood, so everybody's sitting in the same neighborhood but flying apart. Okay, so that is the delicious contradiction. That, it's like you're forced to be a neighbor, but you are Your natural tendency is to run away. And here is the last general slide. And I stole this from the University of Maryland. So this is a cat map. I thought I'll have the cat map because quantum mechanics is forever having its cats, and they're doing wonderful things with cats. But I thought that we too have a cat, and though we're doing something somewhat violent to it, we are almost mangling the cat in one iteration. Now this is the map. See how simple it is. It's just a 2x plus y here and a x plus y, but mod 1. Mod 1 is important because that is what folds it back. So here is a pixelated picture under one iteration of this map. This map also, just to put it, for completeness, is an invertible area preserving map. So that means it has a unique inverse, and it also, its determinant is 1, so it preserves areas. So, but what does it do? So the first action is to pull it. Okay, the cat, still sort of identifiably a cat, unfortunately skewed and pulled, but still kind of cattish. But the next operation cuts and folds it back into the square. And in one iterate, the cat, poor thing, looks like nothing. Okay, so this is the power of chaos, that you can actually, in one iteration of a map this simple, take something and make it almost unrecognizably different. Okay. So now to what I really wanted to talk about. So the thing here is that this people have been accruing a lot of knowledge about this field, and in some sense, perhaps the field has progressed enough now to warrant payback. Okay, so this I learned from my friends in the US. Everybody wants payback to applications. So when the field is still, in the stage where just people are getting a handle of understanding new concepts, perhaps the cry for payback is not that large, but it becomes larger and larger as more knowledge accrues. Okay, so in some sense, I think in this field, time has come to flip the question. So again, to put a spin on a favorite quote, probably it's time to ask not what you can do for chaos, but to ask what chaos can do for you. Okay, so we ask the reverse question and see if we can make some headway into that. So that would be the rest of this, my interaction with y'all. Okay. So you can always say these words, harness the richness of chaos. I love using that phrase, but none of this makes sense unless you can give to the practitioners, who are most often engineers. Engineers are a hard set of people to win over because they want something direct, they want something efficient. Okay, they're not so interested in something beautiful. Okay, that's not their lookout, but it should be neat, direct, and efficient, and in some sense controlled, because they have to do it over and over again millions of times without failure. We understand it, we use that sort of reliability. So what I will show are these two things. So one is the use of controlled chaos. So this uses strategies to extract a lot of temporal patterns from the underlying dynamics. So the first approach will be to use control, and the second one, which is my more recent thing, and I like it more. It's been going on for the last 10 years or so and continuing in some fashion, is the interplay between noise and nonlinearity. So in the last 20 minutes, what I'd like to tell you all is that I have kept noise away from this equation, but I will bring it back. It started with uncomfortable questions people asked us about noise. And then again, we found that we could flip the question again and say, maybe if there is ambient noise, we could try to use it as an engine to work for us. So I'll try to show these two things. Okay, so the control thing. There are many control things. I will just tell you the one which is mine, People I like it because it's something which I thought of, and but maybe there's a better reason too. The good reason for this control is that it is very simple. I can actually define it in one line. So it is a scheme which is actually there in one line. So what is the scheme? It says if there is, so we don't care so much about the dimensionality of the problem, but maybe say 1, 2, 3 dimensions in your head if you want to fix it. But I take one variable, x, call it x, and I follow it. And if this x exceeds a prescribed threshold, then I just pull it back. I reset to x star. So there is a prescribed threshold. I don't allow my system to wander beyond the threshold. I pull it back. That's all. So if I had to write a program, it would be if x greater than x star, then x equal to x star. If it is an electronic circuit, there'll be a precision clipping part there, which will do this very easily. So that's it. But though the method is simple, what it does is actually quite deep. What it does is this small limiting of the dynamic range of your system clips your chaotic orbit into cycles of different orders. So you can actually generate now stable desired patterns from this chaotic system. So think of it this way. Here is a chaotic orbit, doing something very complicated. I sort of snip one end, put a little wall in your phase space, saying it's like, in Indians know this word, Lakshman Rekha. So, can't go beyond this. I will pull you back. So I just put a little hard wall there. It could be very tiny because it's allowed to do a lot when it's under. It does whatever it wants. Just at the end, you pull it back. And this little action actually stabilizes it, not just stabilizes it into a pattern, which is wonderful in itself, but by changing this level, I can generate patterns of all orders. And why is chaos fun? It has this advantage that embedded in the chaotic trajectory, there are temporal patterns of all kinds. So you can think of these different kinds of patterns there, which you can clip and stabilize. So you sort of, I like this portion, I can clip and stabilize it to that portion. Obviously, if your dynamics didn't have all these beautiful patterns, you could do nothing. I mean, you could do a limited amount of thing rather. But because it has all these things, you can do a lot with it. So, for instance, if I took this chaotic logistic map, I showed you a iterated function system, in one of those early things, which looked very complicated, right? It looked pretty much like noise in fact. So I take logistic map, say at that parameter r equal to 4. And then as I vary the threshold, I get all these different things. I've shown you some. Actually, you get literally periods of all orders. So you get fixed points, you get period 2, period 4, period 6, period 7, 9, 10, everything. So what you can find is that it's like a lookup table. This is what engineers love. You give them a lookup table where you put on one side threshold, which they can set, by like, as a target, and what you will get on the other hand. Okay, so this is a one-to-one correspondence between the threshold and your controlled orbit. And here is an experiment. So I thought instead of showing the guts of the calculation, which is very long, I'll show you 2 slides of the experimental verification, because everyone believes oscilloscope trace more than the calculation. So here is the chaotic trace, and here is a 6 cycle. Okay, this was done by my experimental friend, a long-term collaborator, Murali, in Anna University in Chennai. And but the fun thing here was that I would actually tell him, put this threshold, and he will come back the next day saying, yes, I got the cycle. It was really, literally, the theory came before the experiment. In terms of theory, you can actually show that when you do this thresholding operation, however simple you might think it is, you actually trap the system in a super stable orbit. And this is super stable because you can think of it this way, that at the point at which you are thresholding, your f prime becomes 0 because you're putting a hard wall. You are actually, it's a flat portion. So it's like a flat top of your map. And because of that flatness, by definition, because f prime is 0, it becomes a super stable orbit. So that little part makes the entire set not just a stable, but a super stable controlled orbit. And there's a bit where you can also realize that because of the ergodic property, you are sort of guaranteed that at some point in time, if you have put your threshold inside the attractor limits, you will exceed the threshold. So you are guaranteed control because of that. I just thought I'll put those things. They are sort of theoretical constructs, but they help to make the practical part of it go through. So what do
Can
you
I
get
ask a
out of
question?
this? Yes, please. Yes, yes.
How important is it to have a hard wall there?
Yes. So the hard wall is one of the easiest things to implement, of course, partly because, as you could see, it's just a if then else statement or a small, precision clipping circuit. So it is, you could try this, for instance, there are versions of it, which I saw later with intermittent control, we also did it, putting it at some intervals. So you will have to do the calculation, of course. You will get a different lookup table, but it is possible. So indeed, you need not have a hard wall at all times, as I put it, which is the easiest way to understand it and also implement it. You can also have it in other ways, intermittently or with periodic things. But I would still think that the most robust control one got was with the hard wall.
Okay, thank you.
Partly because of if you think of it, what did the thresholding do? So suppose you had a chaotic logistic map, the parabola. It actually just sliced off the top. So if your 45-degree line intersects the top, the flat top, then that part is a point on the cycle, and it is super stable because of the flatness. So that is why the hard wall is so nice in some ways. Yeah. But there are versions of it which you can get around the hard wall. Yeah. So perhaps I don't know if that was understandable.
No,
Maybe we will get back to it. Okay, right. So basically, then we can get a whole bunch of stable response patterns. So here I have 1, 4. Oh God, I forgot. 1, 2, 3, 4, 5, 6, 7, 8. I think, and I think this was 10 or 11 or something. So all these cycles you get very stably. So I can now think of the chaotic system. So one chaotic system can now be thought of as a flexible pattern generator. Okay, so you have one object, but I can tweak this one number, this threshold, and make it behave, in these different avatars. So that is the fun part. So I get a flexible pattern generator from this one thing. And this threshold and the control period correspondence is actually can be done exactly analytically for the maps. I should say, though, I could not do it for differential equations, and some other people tried and they couldn't also. So I don't know how to do it for differential equations. Maybe if I make it into a map, and I just haven't managed that. But for 1D maps, it's completely exact. And I will just say, I didn't want to show the guts of that calculation, because that would be half an hour in itself. I wanted to do, sacrifice depth for a bit of width. But I'll just say one thing. The part which is easy to understand to calculate is this. Suppose I have a threshold. I can calculate the control period easily. Why? Because as I said, you will cross threshold. So you have at x star. Then you just have to see how many iterates of the map starting at x star leads to a value which is greater than x star. So once I get this inequality done, then once I solve this inequality, I will have the answer. So that is actually not hard. I mean, it's grunge work. You have to work through everything, but technically it's not hard. The reverse question actually I found pretty hard. So the reverse question is this. if I want a particular controlled period, what threshold do I have to put? And this answer is hard because it's not unique. You can have many different thresholds give the same period, whereas every period has one single control, every threshold has one single controlled period. The reverse question, though, has is multi-valued. So there I would have to do some symbolic dynamics to look at the inverse maps and do some weeding. That was a long calculation. It's there in this particular paper of mine, and every detail is there. The fun thing, though, is that though Murali did it on a clunky electronic circuit sitting on in his teaching lab, as it happened, so very low tech, though all these things, all these figures are from that low tech device. People then carried it forward, and as far as I know, some of them did very well. I probably don't have the latest, but Morai's group in Kyushu have done it for at least 120 on a tiny CMOS integrated circuit implementation. So literally they can pack it into these IC circuits, and so it works. It's literally the same principle, but it can be scaled down. I don't know how they do it, but they claim it is pretty much the same idea. So the next thing is a slideshow, just to convince you that it works for things other than the map, though I don't have the theory for it. But I do have the numerics and I do have the experiments. Okay, so here is a nonlinear third order ordinary differential equation, which looks like so. Okay, these are the circuit experiments corresponding to it. So here is what it would look like given, no control, going its merry way. It's a single scroll chaotic attractor. Now, as I put different thresholds, I get different controlled orbits. So here is one. As I make the threshold a bit larger, I get this. A little larger, I get this. So it works. Here is the good old Chua circuit, which a lot of students would have seen in their electronics lab, maybe. And so this is a double scroll. And here again, as I put my threshold, I can get a fixed point. I can get different orbits of different periodicities. So we got a bit excited and we said, okay, all this time we are doing an intervention on one variable. So here also they were actually underlying it, there are three variables, okay? But I'm still doing an intervention on one. So let us try our luck and do it on a hyperchaotic system. So this would be a fairly stringent test. Because, why? Because more than one positive Lyapunov exponents are there in this system. So you can think of it as a system where there are more than one unstable eigendirections, which have to be reined in, which have to be sort of controlled. But so the question is, can I threshold a single variable and do it? Honestly, again, theoretically, I don't know the answer. So we just jumped in and did the numerics and the experiment. And here it is. Here was the hyperchaotic attractor shown on two. It has four variables, but this was on the V1, V2 plane of this, on two of its variables. And this was a particular controlled orbit. This was a very fun system because you could get literally a gallery of very pretty pictures of different kinds of controlled orbits. Because, as I said, the more it has, the more it gives. So the more interesting patterns it has, this library of patterns that you get is, of course, very large. Okay, now that's nice. I mean, at least felt very nice. But can we push it one more step? So the next bit is to ask this question. Can we somehow use this control system to do something useful for us? And what's more useful than computing? So in some sense, the payback is that, the computing machines essentially helped us, or the technology essentially helped us understand chaos. The whole breakthrough in chaos theory was fueled by computers. So now can we sort of use this understanding to further power technology? Okay, so this is chaos for computation. So what is it that we want? So what we want to do is use this threshold activated chaotic system to act as a logic gate. That's what we want. So this is the aim. We want to implement all the basic logic gates with a single chaotic element, and it should have this ability to switch between these different operational roles. So we know that people build machines out of families of NAND gates or NOR gates, but it would be fun if you could actually have at hand a whole bunch of hardware which could be programmed on the fly. So it would have a sort of flexibility like programmable field programmable gate arrays, which could maybe work as arithmetic processing units or as components of memory, whichever way you want to partition it. Or you could optimize it for application specific things like an ASIC maybe. And of course at the end it also should have general utility. It should be able to do what a standard CPU does. Okay, but more flexibly, and should be reconfigurable. That's the task. So let's go back to the same old chaotic map, maybe the logistic map. And I do one step because all I need to do is have a way to fix inputs and have a way to understand outputs. So inputs, all I say is, okay, it's at X naught. Inputs is given by the world, whatever the user wants, I1, I2, binary units, and I add it to my state. And the output is just obtained by the threshold mechanism after one chaotic update. So if the f of x, which is a nonlinear function, okay, if it is greater than x star, which we have to design, then it's output 1. If it is less than x star, it's output 0. Simple. So output is from threshold mechanism, state is just additive. And what do I want? Here is, say, the truth tables of basic logic operations, which you know from your electronics. And here are your set of inputs, binary, 0, 1, 1, 0, etc. And these are the outputs that you want, desired outputs, which are the logic functions which you want to implement. So if I translate that table into equations, what I get is this. So if my chaotic system has to behave as as these logic gates, what are the necessary and sufficient conditions? So that is what is given here. This set of equations are the set which we need to satisfy simultaneously in order to do this task. So these are necessary and sufficient conditions. And the bottom line here is that the robust solutions of those necessary and sufficient conditions exist only when the system is sufficiently nonlinear. So this is where nonlinearity to the rescue, of this task. So the nonlinear dynamics, essentially in some way you can think of it as the richness, because that is what allows these solutions to exist. And also, of course, the determinism. So that will allow us to design it. We can actually do the reverse process. So this is what has allowed us to select all the different responses from the same module. Okay, so this, of course, we put to the physicist, put to the engineers in IEEE publications as well, and also a whole bunch of patents. A couple of them are shown here. Okay, and here is a picture of it. So we think of this as a morphing or a reconfigurable logic gate. So same old chaotic element, but if I give it a different threshold, it can behave, say, as a NOR gate, which is a fundamental gate out of which all logic circuits can be built. And if I want to switch it, I just switch the threshold and it behaves as a NAND gate for as long as I want it to behave. So I can essentially morph between logic functionalities because of this flexibility which dynamics has allowed us. We can also use not just changing thresholds, We can also keep the threshold the same, but tap the response of the system at different times. So either you can change the threshold, keep the time same, or you can keep the threshold the same and change the iterate at which you're tapping the output and get the whole gamut of logic operations. Okay. And this is a company which has been developing this. It's actually sold out to ARM in Cambridge now. But I hear in the business, selling is not a bad thing, apparently, if it's at a good cost, I suppose. And they had several generations of it, though they are looking for more what they call ASICs, application-specific integrated circuits. That is their thing. But, so the whole point is something which was just tinkering around with maps, doing symbolic dynamics on them, and just doing some exact calculations, has found its way into something which is, almost unrecognizable even for me. Okay, right. So the last bit, 15, maybe I might just take a couple of minutes more. That's it. So I thought I should also bring in this new thing, which the new thing always makes you more excited than the old stuff. So the things which I've been more interested in of late is the interplay of noise and nonlinearity. So before that, noise was just there to check robustness, to check stability and stuff like that. But I had not actually sort of looked at it as an opportunity. So many people ask me in conferences, is it robust with noise? What's going to happen if your chip heats up and stuff like that? And, you say we have done checks and all that. But then, when you think of it a little bit more, the first thing is, of course, that the noise characteristics cannot be suppressed or eliminated. So you cannot wish it away. It is something you will have to work around. So you might try to keep suppressing it, but maybe you can work backwards and see, given a noise floor, is there some way to tweak the nonlinearity to get the best operation? Okay, so noise is what you can't wish away, but can you do something with it? That's the idea of this last bit. And this, of course, has basis in old and well known to many of you concept of stochastic resonance. So I will just put it in one slide. So if I had to say it in words, it would be the cooperative behavior between noise and dynamics. And this actually will produce, again, interesting and counterintuitive physical phenomena. So one of them, for instance, is that the appropriate amount of noise can boost signal. And in fact, it can facilitate detection in a noisy environment. And apparently, people, even in biology, naturally it has evolved. And engineers apparently did it all the time. So when I first gave this thing, they said, oh, dither noise. Of course, we added, that's how your speaker, what you hear is so crystal clear, etc., etc. So this whole thing of signal to noise ratio being maximized in the presence of non-zero noise is interesting, of course, in itself. And it has been demonstrated in many, many places. So what we were searching for is a similar phenomena. But now we want to ask the question, could we find an optimal band of noise where the output is a logical combination of the input signals? Okay, so now I'm not doing SNR, which all the engineers do and lots of physicists also do, that is signal to noise ratio or information transfer thing. There, the way most people have done is that they take a system, say a bistable system, and then they would hit it with a periodic force and then see where your signal to noise ratio peaks. But we are not asking that question. No periodic forcing. The world gives you a random set of inputs, whatever the world wants, the user wants. But what the system should do is to give an output which is a logical combination. And the question is there an optimal band of noise where this happens? And so naturally, we called it, perhaps unfortunately, because this word now is everywhere, we called it logical stochastic resonance. And so I'll just show it for one simple example so that that fixes in your head. Of course, it's done with many complicated examples. So take a simple nonlinear dynamical system, not chaos, just nonlinear system. Okay, so here there's an f of x. It's a nonlinear function which gives rise to a potential with distinct energy wells, say a double well. Okay, I is what your input signal is. It is low amplitude. So on its own, it might go undetected. It's a very low amplitude thing. Remember, in all things, we want to work with low amplitude. That's a good thing. And then there is, say, additive noise. Okay, now this low amplitude signal is your I1 plus I2. So, and I1, I2 are binary. So 0, 0, 0, 1, 1, 0, 1, 1. And so it can add up into 3-level aperiodic waveform. So because there are 2 independent input signals, comes in any random order, it's a aperiodic waveform. So say, for instance, you take this simple cubic nonlinearity. It has 2 wells, one sitting around -1, one sitting around +1, bistable, simple. Physics 101. The output of the system is the state, the well it goes to. So say one well is 1, the other well is 0. So the logical, so if it is hit by these input bits in the presence of this noise, here is your nonlinear system. It should react in a way that it should sit in the well which defines its logic output. And here is a picture. Even if nothing else stays, I would like you to just remember this picture. So these are increasing levels of noise as the panels go down. This is very low noise. Okay. And as you can see, and this little square thing looking like an aperiodic step function is your input. You give any old thing to it. And this furry thing here is the response of the system. So it sits in the lower well ones, sits in the higher well ones, goes down. But if you look at this, you see that it's not consistent. Because once in a while it gets stuck in the top well, it doesn't come down. It should come down because, it was at this level here, but now it's stuck here. So this is no good because it's not reliable. It's not doing consistently what it should do in response to the inputs. Now let me skip to the high noise. When I look at the high noise, this is also no good because this is terrible. I mean, it's just hopping back and forth and, all over the place. And the noise essentially overwhelms whatever could be thought of as a signal in this case or an output in this case. However, there is a sweet spot in between where it actually reacts to the inputs reliably. It does exactly what it should do according to the truth tables of the logic. And it is not jumping back and forth randomly. So it has, it has the probability of getting the right answer, the right output is practically 100%. So there is indeed an optimal band of noise. Okay, so the crucial observation here is that the logic output is obtained consistently and robustly only in this optimal band of noise. For very small, very large noise, it does not give consistent logic output. But in the moderate noise, it gives it absolutely spot on. Okay, and we went on and, of course, verified it as we have always done. You could also try to see if you can marry some of the ideas we had before of a morphing logic gate with this. So we added a little constant bias, really easy to do in experiments, just a constant bias. But what does it do? It actually changes the symmetry of the potential well. It swings it in a certain way that you can actually morph between logic gates by this little swing. Okay, so here is a summarizing picture, which took me very long to actually do, because each pixel here is about 1 million runs from a stream of random numerical inputs. And this is the probability of obtaining these logic operations. So this nice bright spot in the middle is good. It's almost 1. So probability 1 of getting the right thing. What I have on the axis is the noise on the x-axis. So you can see that this spot is in some moderate window in the middle where it does well. Low noise, no good. High noise, obviously no good. And on the y-axis, I have this asymmetrizing DC input. I've called it DC because of a little bit of the circuit thing, but basically it's a number, a bias, and it is the one which swings your well and makes your NAND a NOR. So it is your handle to morph logic. So you get noise enhanced logic and morphing logic. And I thought I'll show a couple of pictures, just like a slideshow, of things which are done in experiments. So after we got this out, Mohanty, who has a nice lab in Boston, I don't know, some of you might know him too, he has these nanomechanical oscillators. Okay. And then he was telling me that these things have these two vibrational states which coexist. I said, God, you are absolutely set up to do logical stochastic resonance. So why don't you just, because it's sitting in his lab, fabricated from a nice single crystal silicon with, their lithographic techniques. And it's very small and it has very low power consumption. So what he did was he hit it with the whole stream of inputs and managed to get exactly what we saw in that very simple example with a bistable system in this much more complicated example. So these are experimental traces from his nanomechanical oscillator. Bottom line is the same. Lots of noise, no good. Low noise can get stuck in the wrong well. So sometimes it just can't hop. And moderate noise, perfect. I also thought I'll just show you one more small thing. This is actually numerical, this and analytical, but not experimental. This was done with my friends in Japan, Kazuo Aihara and Ando, who was then a student. Half of his thesis was this. So here we tried to play around with this. I love this EPL cover of this. Those artists are so good. I wish I could have done this myself. So these are actually null clines for people who are in nonlinear dynamics. These are null clines. And where these null clines are intersecting are these 4 fixed points. So remember in the bistable, you had 2 fixed points to play around with. Now we are coupling these genetic networks to play around with 4 fixed points. So that gives us a lot. So you can actually go around these wells in a way to get what you want. So those were null clines. So I'll just show one thing. So one of the things we got from this was that we could get 2 gate operations simultaneously. That is, we are getting parallel computing. So basically, one of them could give OR, the other one could give AND, for instance. Or one could get XOR, one could give NAND, whatever we want. So because we had these wells, so now we had more to work around and we could get more gate operations. You would need 2 wells per gate operation, of course. So with 4, we could do 2 gate operations simultaneously. So that was somewhat fun. And later on, Ed Helen and, I was also on this paper, and his student did circuit electronic analog of this synthetic genetic network. Apparently, it took them a lot of time to do. So I should give them credit because I don't know how they actually set it up. They send me the circuit diagram, but this is low noise. And as you can see, bad, because though you're hitting it with all kinds of inputs, either it's stuck at the top or it's stuck at the bottom. No good. Moderate noise, it is exactly switching the way you want it to switch. So very good agreement between circuit experiments and the prediction. There are a couple of popular blurbs on it, which was there in Physical Review, Focus, and Science News. I just thought I'll put it there because though they're a bit imprecise, I think they probably say it with more jazz than I could put forth. Okay, so I think I'm more or less end of my hour, but if I can just take 2 minutes, is that okay? Should I just 3 more minutes?
Sure,
Yeah. So I'll wind up in 2-3 more minutes. I hate
Thanks.
to take more time than is given to me. So I thought I'll show one slide of work from other groups, things I understand insufficiently, but I just picked up a few. Some of it is theoretical. For instance, people immediately, a whole lot of them actually work in China too, picked up colored noise, all kinds of time delay, stochastic resonance, other information-based measures, bit error rate, for instance, to characterize stochastic resonance, not the ones which I've already shown, but other things, as I said, like bit error rates. They tried, many different things. A whole bunch of experiments too, with VEXELs, with micro and nano electromechanical systems, plasmonic resonators. I saw some stuff on thin films. I really didn't understand it, but I wrote it down. But they said that they have done this too. At least the graphs looked like a logical stochastic resonance at the end of the day. Okay, so just the last 2 minutes, I thought I'll just tie the first half, first 2/3 and last third. And so what we thought was, so the first part had chaos. Second part had nonlinear systems, but no chaos. It had noise and nonlinear systems. So they were multi-stable attractors, but like, 2 fixed points, 4 fixed points, but not chaos. Then we thought, why can't we put chaos and this sort of hopping together? So of course we do know that not only are there multi-stable fixed points, there are also multi-stable chaotic attractors. So what if the chaotic attractor is what you hop in the logic operation? Is there something to be gained from that? Okay, because what if you could switch between chaotic attractors as a logic operation? So here are, for instance, 2 chaotic attractors which are coexisting in your plane. So if I start here, I sit here. If I start here, I sit here. And as I give these appropriate inputs, my system can jump from this chaotic attractor to this or back according to logic truth table. So that is what we showed, that not only can you have simple attractors like a fixed point, for me is a simple attractor. So switching between simple attractors can give you logic, but switching between complicated attractors, like switching between chaotic attractors, can also give you logic. And is there anything to be gained? I mean, it's fine. It gives you logic. Good to know. But what we gained was something which we haven't still fully accounted for, is that the input signal could be 3 orders of magnitude lower than the size of the attractor. So basically, extremely small change of system gives an extremely large dynamical output. So this sort of ties up with the idea of tipping points in dynamics, where you sit very close to another attractor in multi-stable things, and you can just push it off the cliff into the other one. So you need the tiniest of pushes to get a very large outcome. And this actually makes people interested, because low amplitude is low power and you get a lot out of very little. So this is why you can think of it as a generalized logical stochastic resonance, because you're doing the same thing with a complex attractor. And it indeed works. So these are actually not fixed points anymore. They are now chaotic attractors, if you zoomed in and saw it, which I'm not doing now. Okay, so this is a kind of summarizing slide of this, that essentially the amplitude of the logic input signal was very, very low. And in the experiment, for instance, I mean, it was about 10 millivolt, which was about 100 times smaller than the typical experimental noise, which was about a volt. So it was actually smaller, way smaller than even the noise. So it worked, and that part was interesting. So very low amplitude inputs give high amplified outputs because of the tipping phenomena. Okay, that is my last slide, and I can take questions now. So this is the broad outlook and outreach. So I just thought I'd share with you that nonlinear systems are abundant in nature. I didn't say that, but if they are so simple, there's got to be lots of them. But they can actually be very readily engineered. That is true. And the central idea was to try to use it to do something like a computing device, logic gates. And rather than suppress the chaos, the whole idea was to use the opportunities. And what was the opportunity it gave us? It gave us all these flexible pattern generator. So you could design the responses to get whatever you want from the same unit. And the last part was to use the noise and the nonlinearity, again now to exploit the opportunities of noise now to get more reliable logic operations. Okay, so I'm done now. I'm sorry, I was a little bit over time, and I'm ready to take questions. Yeah.
No problem. That was a great talk. Thank you so much. We are open for questions. So
yeah,
if you have questions, we can take them now.
Yeah. Can I ask a
right.
question, Suraj?
Yeah, Yamuna, go ahead. Yeah.
Nice talk. Thank you.
Thank you.
The question I have is, how would you extend this to spatiotemporal structures like flow patterns?
Right. Yeah. Yes. Right. So that is indeed a very, very nice question. So, for instance, we also, so what is tempting is that there are these results where you have kind of coherence resonance in extended systems, where you can use the use noise to enhance structure. The only thing which so maybe I've gotten to a little bit of a rut here, and I should be a little more open. The control part of it is a little less easy to do when you have spatiotemporal things. I have seen papers of people using fluid, microfluidics, for instance, or even fluids, and even somebody had something which was really interesting, which not my work, somebody else's. They had these. What is that creature called? It's like a blob of something, which moves, and they're trying to map it to logic gates. So all of that is very nice and interesting, except of course in terms of it doesn't interest the engineers yet, because its time scale is very slow. You can't you can't do the operation fast. Control is a bit weak. So these would be two things to address before we can get an engineer invested enough to make a chip out of it. But let me just say this. That thing which I said, which Morai's group has done in Japan, that is actually spatiotemporal. I didn't say this.
Oh,
They had actually coupled those 124 maps on a single chip, 124, 128, some such, on a single chip. So they had actually done a spatiotemporal thing. But they hadn't used it for anything, because I don't have an idea. So I've been trying. Sometimes I feel maybe I could use it for a search operation, because suppose I put all the inputs of your database into a thing, and maybe the collective response is like a yes or a no, is a needle in a haystack kind of thing. I haven't done it as yet, but I do know that they can implement it, but I don't have a killer application for it.
Okay. Thank you.
But it's actually an open thing, and I feel yeah, especially if you could do it, maybe fluids, for instance, if you could do it, it would be great. My understanding of fluids is not very good, so I mean, I can't work through all the nitty-gritties of it. But I've seen it. Some group in Hungary, I've seen them do it.
I see.
Yeah.
Thank you.
Orjendu, you had a question.
Yeah.
You are
Yes.
muted, huh? Okay.
Yes.
Yeah.
Thank you, Shruti. Yes. Right. Thank you very much. That was great, and thanks for welcoming me back into this group, which I know from so many different places. But I had a question: is it possible to, because you're using probabilities and noise, and you're sort of intrinsically driven towards thinking about distributions, is it possible to understand your work as manipulating some sort of non-equilibrium metastable distributions?
Absolutely.
Because that's what you're really, in some sense, working on. You're doing non-equilibrium thermodynamics in some sense in your logic gate system. Right. And this sort of connects back to Dr. Gevenu's work also. It's in that question.
Yeah. So this is absolutely spot on. So in that EPL paper, for instance, we have calculated exactly, as you said, the probability distribution from the Langevin. Essentially, what we have to do is to show that that probability distribution sits in the, almost, with pretty almost probability 1 in the part where which we have defined by our logic gate. So that calculation is actually not hard, because the system is not that hard. And even for the synthetic genetic network where we did it exactly, there also it wasn't very hard. So and you're absolutely spot on. So it is a question of probability. And so the part where you are doing the engineering little tweak is to put your output what do you call it, definition such a way so that the probability sits nicely, almost 100% in the corner you want it to sit.
Right. I mean, I'm saying so I mean, a very abstract way, which I can't think of it, but it's like you're manipulating the Koopman spectrum or some spectrum to get the right results for your logic.
Right. You're tweaking it so that you want to push it to the point which is desired by something. So in this case, I have desired logic gates, but suppose you had a different killer application, like as I was saying, search, which is in my dream application. I haven't mapped it to it, but if you can somehow manipulate it to map to that would be another killer application. But yes, the underlying thing is exactly that.
Ambika, you had a question.
Oh yeah.
Yeah.
Hi Ambika.
Hi Sudeshna, nice talk.
Hi. Yeah.
So my questions, couple of questions related to the first part of your talk. So you were talking about clipping the logistic map, and if I understand correctly, it's actually stabilizing the unstable cycles in the chaotic region, correct?
No, Ambika. Actually, that is why it's so different from OGY. So they actually literally. So, I know everybody asked me that when I was young. So, I mean, I shouldn't have said that, but whatever. So basically, it is absolutely true that the most famous control method is to take the embedded unstable solutions and stabilize it. Now, they actually do a terrible job in real life, because a person who's trying to stabilize these things has to do so much work to actually get there. So many perturbations you give. This is absolutely not it. So none of those are actually solutions of the chaotic thing. So that's why, so when I saw, I got 1, 2, 4. Then I said, Abhi to, now I'm going to get 8. No such luck. The next one was 6 or something. So it's like, so then I said, oh, this is something completely different. So then when I did the analysis, I realized it is not, the sequence is not coming from, the sequences we know, and it's not period doubling. It is not unstable solutions of the map. It is actually generating a whole new family of new super stable solutions. So that is the fun, that is the interesting part. It is not stabilizing an unstable solution.
Okay, so in that context, have you checked what will be the MSS sequence of this? Because you talked about
yes, absolutely. Right. That is actually that whole PhysRev paper, some 25 pages of it is mostly is MSS sequence. So the whole thing is to do, because as I said, that the second question, which was hard, was to say, if I want a control period, what threshold should I put? To get that answer, I had to get those sequence. So the sequence was, I had to generate it to get that answer. But because of that, so that is actually, so basically you take it and you get this 2 left-right sort of inverse solutions, but and then you do combination, except you have to be careful, because there's a masking of a certain family of solutions. So little bit of, it's not exactly as we have done in textbooks. So little bit of care has to be done, but yeah, that can be done.
In the
I should also mention,
that
one I don't know. Ambika, I didn't hear your question. Sorry, I jumped.
In the hyperchaotic system that you considered, there also you said you are getting a large number of patterns.
Yeah,
but all these patterns are also not normally there in the state of the system. Is that newly generated thing? So
they are all looked, I mean, we never saw them like you would think that maybe I sweep some parameter and I get these things, so later on I see them as stabilized thing. No, they were actually, in fact, the fun part was we were putting in various things to get weird pictures. So, we were wasting time doing it, of course. So it was all kinds of pretty pictures, but none of them were anything we could get by sweeping any parameter. So it's the same thing. It generates these orbits which are not actually orbits of the hyperchaotic system at any other parameter or an unstable one either. So it's not embedded unstable thing.
Okay, so that's it.
If I could understand that, it would have been good, but that part I don't understand fully.
Okay, thank you.
Yeah. Okay.
Surajit, I have a question.
Yeah, go ahead, please.
Sudeshna, great talk, very, very enjoyable talk.
Hi.
Recently, people are talking about this reservoir computing.
Yeah.
There be some connection between this and what I think there may be, no?
No, not really. I don't think so. So, actually, since I wanted to try something new in my sabbatical year, I also did some machine learning stuff in the last year. Not reservoir computing though, but I did look at their work. It is actually quite different. It is quite different, partly because they are trying to tweak either weights or so one can think of it this way. They are and also, of course, to get a set of inputs, they have a huge reservoir. So here we have one unit which is giving you all this patterns. So we don't have a reservoir of it. Reservoir is like a whole bunch of them. And also I was talking a bit with even I don't know, some of them who do it in Maryland, for instance, Ott or Tom Carroll and all. It is not very clear which nonlinear system or what type of connections are giving the best things. So everybody is thinking, how to make it a bit systematic. So right now it works exactly like a standard machine learning algorithm. You have the reservoir, you give it inputs, hit it, see the output, minimize loss, see how well it does, tweak. I know I've been doing it also. So it's a legitimate exercise, but the dynamics of it is not clear. Whereas here, actually, the dynamics of it is exact. I mean, that part was done before all the applications. I mean, that is exact. So it's working upwards here, and there it's working downwards. And I don't know. I think it's still there's a gap there. This is my understanding of it so far.
Thank you.
Okay, there is a question from Hemchander. Let me read that because his microphone is not working. Can these ASICs devices create and compute hashing functions for blockchain applications? That's the question.
Yeah. Okay. So first, I should say that whatever answer I give you is not going to be very satisfying, and the reason is I don't know it very well myself. Okay. So the reason is, I mean, I partly some of it is it's so difficult to get. Because it's not open knowledge usually, but indeed I think this is what because now the company is sold to ARM, this is what they sold. I mean, their basis of their selling was that they could do this efficiently. So how well they have done it, how well they fare with respect to existing thing, I don't know. Because it becomes completely commercialized now and it's in a different domain, and I don't know. So I wish I knew exactly. So the broad answer would be that I'm sure one could do it. How efficiently, how well, how much has already been done, I'm not completely sure, to be honest. But I do know from what they were saying that this is what they bought the patents for. They think they can do it very efficiently. They are looking for some specific applications, but that part is commercial. So I don't understand it too well. Sorry, it's a bad answer, but I can't, give you too much more on that, unfortunately.
Yeah. There is another question from Ronnie, and here is how do the Geologic chips processors fare against the presently available processors?
Yeah, it sounds like more or less the same question. So it will be my bad answer again. So they had been taking the first few generations of the chip to various trade fairs. So what happened was, I sat in some of the, so because this is a little bit on the business end, so I did sit in some of their meetings. So what they said was that it did well for power, it did well for size, it did well for speed. So I said, what's the problem? All of this sounds like it's doing well. What they said was that the process of manufacture needed something which made it very expensive. And so they had to tweak that aspect. So in terms, so that is, so I learned a lot in this process. I learned that it's not enough just to be smaller, faster, low power. You also have to be competitive in terms of the manufacturing process, which I didn't know, and I absolutely still don't know. So the only way to work around that is to use processes already there and to see if they can implement this with them. And this part, I actually, I mean, it's they're working on it, and they are getting somewhere presumably. Since they're generating some money, but I'm out of this part. It's too engineering for me. It stopped interesting me too much. Yeah, sorry.
Yeah,
no problem. Ronnie had another question.
Sorry. Yeah.
So can I ask?
Yeah, go ahead and ask, and then we'll move to.
So I have a doubt that so this chip is there, and then we have to give it instructions, right? And so the instructions also then need to be very precise. Otherwise, since in my understanding, since the chaotic system is very susceptible to any small change, then it will give some other result.
Yeah, this I can answer actually, because this one had to be checked. Because indeed, if it was so sensitive to input things, then we are not in business, right? I mean, this is no good. So the whole thing is that when you do this, which is why I was trying to say that in the beginning, that in when you do it, you have to give them a controlled algorithm to do it, where the what you're suggesting should be extremely stable. So what I'm saying is that the pattern generator, which I'm saying, that is actually stable. In fact, it's super stable. That is very stable, though it is generated through the chaotic system. So that's why there are these contradictions. So you can cleverly think of some mechanism to generate these stable patterns out of a chaotic system. But do remember, this is one update only. So it's not like it's going on for a long time. So if you suppose I wanted to tap 3 iterates, I will do much worse. So this works extremely well because of one iterate. So it's almost like one nonlinear function. And there, because you take the part of the operational range which is wide, of course, we have done all the noise tests, everything, sensitivities, all of that. It's, the experimentalists do it all the time. They have to, otherwise it just won't work. So that part works. But the key here is that it's one iterate. And so the one where I said that, you could use time, there I was not being fully honest, because if I use more than 2-3 iterates, what you are saying absolutely is the problem. That your operational thing gets narrower, and your sensitivity gets, so you might be thrown out of your good operational range. So there is so I would say, so the engineers go for one update and changing threshold. But for a physicist, it's nice to see that you could do it with time as well. That is all. But practically, after 2-3 iterates, your range will become very small. I might show it here. 1 minute. Just sorry. It's that colorful picture here. Sorry, this one. Oh, this one. So you can see that the operational ranges are becoming very, very narrow. So you can interpret this as that this is a nice operational range, and so here it's forget it. I mean, no engineer is going to touch. But up till about 4, it's actually pretty okay. But so maybe, I don't know, it's some sort of answer to what you were saying.
Yeah.
Subbu had a question. Subbu, go ahead.
Yeah, thank you. Thank you, Sergio. Thank you very much for the talk. Enjoyed it. So I've got two questions, if I may. So the first part of it, in all your control, are you assuming that the observations based on which we control, are they idealized? Because I'm trying to understand it from a control theoretic standpoint, where typically you've got observations which are noisy, which happen based on sampling on a different time scale. And then you use that information that's fed back into the system to achieve your control. So in this, are we operating under the assumption that we've idealized observations? That's my first question.
Right. Yeah. So that's, of course, a very important question. So if so all of these were tested for noise, both in what you observe, and and also I tried for different sampling rates. I have not shown all that, but it's a lot of grunge and lot of one has to be very careful. I totally understand your question, where it's coming from. Of course, in electronic circuits, because there's that precision clipping circuit, you don't actually have to observe anything. You just put the clipping circuit and you're done. It's so easy that people. I mean, when I later on people said, "Oh, if we knew it was so easy, we would have done it." But as it happened, so there actually we have not, we don't have this observation intervention kind of thing. But theoretically, of course, and numerically, I did check. It's a respectable range of of noise which it can tolerate, and so there we also have something on the fault tolerance, or it's where we had done it systematically. Yes, but it's a spot on question. Yeah, I understand.
Yeah,
without that
yeah, and probably it's because of the system that you're dealing with, those gates, where that is
right.
So the second question is, I know you mentioned about colored noise and other types of noise where you get that ideal noise intensity, where you get that resonance kind of effect, right? I know you mentioned that there's work of other groups, but would you have any insight on how important the particular type of noise, for instance, not delta correlated, but some exponential correlation, something like that? So
correct.
Any insight on how that might affect the resonance effect?
Right. I think I can answer that in one line. It was an easy answer, at least for me to understand. The bottom line is it didn't make much difference. So of course it changed a few things, and the range and the exact noise floor a little bit here and there, but in details. But the bottom line was pretty unchanged. So what they were trying, though, is to increase the range if possible, and sometimes they could, sometimes they couldn't. But but thing is that ballpark was the same, I think. So these were almost like checks of generality, which worked out.
Right. Thank you.
Thank you.
Great. I had a question. It is a different kind of question, the questions that's been asked. And I'm not even sure if it's a good question, but the question really is that if you take many body systems of oscillators, right? And if you were to put hard or soft walls, whether they be amplitude walls or frequency walls, then I begin to wonder what you'll see, because I haven't seen any work on these lines, and I begin to wonder whether you can actually control the complexity of a many body system to something which is much more diagonalizable.
Right. Yeah.
Have you looked
into?
Yeah,
actually, now that you said it, something came back to me. My own stuff, but I'd forgotten. But now that you asked a question, it came back to me. Long back, I tried to take a beam. So that's like a many body, a string of, it was actually a continuous beam, because somebody had told me that they do this smart control of the beam, where they so that it doesn't have huge amplitude vibrations, to clamp it. And so on this beam, it's there in some one paper. So there I did this hard wall, not everywhere, but say 2-3 places in the beam. So it's a continuum with pinned at some sites, and it was a reasonably good control. It depended a bit on how cleverly I placed the control sites. So obviously, if I put 3 of them in one corner, it's a very stupid thing. If I place the controller, so there was a little bit of the spatial geometry of the controller was a bit of an important thing, but it suddenly came back to me. That's true, I did try that one, but I don't know. I should probably go back to this idea now that you all have said it, to something more maybe more interesting thing.
One can even think about by limiting amplitude and or frequency.
See, frequency is hard for them to control. Amplitude is the one they can do easily, because the clampers do the amplitude thing is easy. Frequency is a bit hard, but amplitude, that's also a wall. That's also a hard wall. I mean,
but frequency can probably be controlled through your noise, isn't it?
I don't know.
Isn't it like a soft walling the frequency, or no?
I don't.
Maybe not.
I don't know. I'm not very sure it'll.
Maybe it is more complex than that. I'm just trying to see.
I mean, in a sense, all these frequencies come into play, and.
But one can filter them, I presume, right? One can have frequency filters where you have a cutoff.
So one possibility is to force it. Maybe I'm just thinking on the fly. I don't know the answer. I'm just saying something.
Sure.
So
same here.
it's possible that so it's possible that one could maybe force it with different periodicities or something, and then maybe there is something there. But I don't know.
I can see why you are saying frequency control is harder, because if you want to filter out a frequency, you have to do it very quickly. So you have to very early find out that it's a high frequency or whatever, undesired frequency, and then you got to filter it out. So it requires sophisticated electronics.
Right. And the clamping actually is very low tech. I mean, just as I said, the precision clipping circuit of electronics was so simple. Everyone has it lying in their electronics. In the same way, this clamp is actually very simple. So amplitude clamping, so simple things, they like. I mean, people like
amplitude clamping. I can see the only other way would be that if you embed it in a bath, which automatically filters out frequency. So the system itself is smart enough.
That would be like it's sitting in honey or oil,
exactly.
in some sense.
Right. So that might be, but it still poses interesting questions, because there is this continuous thing that one deals with, whether a system is ergodic or non-ergodic. For whatever it's worth, that's a question that we often want to know. We often want to know whether the system has very large fluctuations that naturally emerge, and if so, what consequences that might have. I mean, one of the things that we find in our work is when a system gets sufficiently nonlinear, you will actually get very large fluctuations in them, regardless of the details. Now, this is a very broad problem. Wherever we have done it, we see it. But when somebody asks me too many questions, I run out of steam because I don't have an answer, right? But this is a question that one can investigate with various kinds of walls. Suppose I start introducing walls in my system. Do these large fluctuations actually get clamped?
Damped, right. So if you have maybe an extreme event of something, is it clamped by just...
you can take a Fermi-Pastor-Coulomb chain of 5 particles and you'll begin to see it after a while. You'll have to evolve it. But if you start clamping it, that gives you a way to look into perturbation regimes versus non-perturbative regimes. And that may have some use there. Anyway, I'm just thinking out loud.
No, that is true. I mean, because that one experience with the beam, I did find that there was it's more subtle because of how you place it, and sometimes you might have a huge perturbation between the clamping things because it just gets squeezed, and so there is more subtlety there.
And these beam problems, beam cantilever problems are extremely important in
Though it did seem to work for a bit, so I remember saying that you could have these embedded controls, smart matter control, but I didn't.
I'd like to, if you can at some point send me the reference for that paper or something.
Sure. This is in some review type thing. I'll send it to you. I wasn't very seriously pursuing it. Yeah, but I'll send it to you. Yeah, others might have better ideas.
Thanks, Sudeshna. Any other questions before we close the session?
Yeah.
Okay. Hearing none, thank you so much. This has been a fantastic Saturday afternoon for us. Saturday night for you.
Yeah, right.
And beautiful talk. And what a way to resume our series after a hiatus. Thank you. Thank you, Sudeshna.
Okay. Bye.
Bye-bye.
So I leave now.
All right. Have a great weekend, all of you.
Right. Okay. Bye, Bhaskaran. Good to see you.